Hello, welcome everyone. I'm back to show the final fifth sem project progress. So water quality monitoring system. Let's move fast because I have explained everything in the previous video. So I'm going to focus mainly on the what have we done in this duration between the previous video and this video. Okay. Outline and introduction, problem definition, objective. All this I will summarize it in a line, sentence. Okay, we are going to make a water quality monitoring system where we will measure five parameters, that is turbidity, pH, EC, TDS, and temperature. And based on these parameters, we will determine the quality of the water, and we are mainly focusing on the drinking water because in the uh, ancient time, or in this time also, we are testing our water in a lab, and its results will come in many days, and it will take time. So we are going to measure the water quality in a real time, and we will see how good the water is, and we will indicate it is safe, or in a risky level, or whatever. um, Objective of the project is to design and implement water quality monitoring system for real-time measurement of turbidity, pH, EC, and temperature, to integrate suitable sensors with a microcontroller and apply calibration and temperature compensation for accurate data acquisition, to provide continuous and reliable monitoring of water quality parameters to reduce dependence on manual testing. So components are a turbidity sensor, pH sensor, electrical conductivity sensors, EC sensor, TDS sensor module, and temperature sensor, and Arduino microcontroller, LCD display, and power supply. We are going to see all the sensors in detail. Okay, let's go to the LGZD turbidity sensor specification. This is my part. Tomorrow I'm going to present this. Okay, this is the LGZD turbidity sensor. It measures the turbidity. Its supply voltage is 5 volt DC. Operating temperature is 0 degree Celsius to 50 degree Celsius. And output is specifications. Output type analog, and voltage range is 0.5 volt to 4.5 volt. And measurement range is 0 to 1000 NTU. This sensor has two ends, where there is one end has a IR LED, and another end has a photodiode or phototransistor. When IR LED transmit the light, when the IR LED transmit the light, if there is a high turbidity, then it will absorb or scatter the light. Then the light reaching to the end of the light reaching to the photodiode or transistor will be low. So if there is a high turbidity, then there will be low voltage, and if there is a low turbidity, then scattering and absorbing the light by the water will be less, and the high output voltage is mm, gained by the photodiode transistor. So high voltage means less turbidity, and high turbidity means low voltage. So this makes the graph visualized by us, that is low voltage. If there is a low voltage, here is a low voltage, and low voltage is for high turbidity, and high voltage is for low turbidity. Here you can see, and there is a turbidity which has the unit of NTU, full form nephelometric turbidity unit. In this way, this sensor works, and let's move on to the another sensor specification. TDS meter version 1.0, EC based. It is a EC based TDS sensor. It measures the total ionic solid dissolved in water. Operating conditions, supply voltage 3.3 volt to 5 volt, and operating temperature 0 degree Celsius to 50 degree Celsius. Output specification is analog voltage. Output type voltage range is 0 to 2.5 volt, and TDS range is 0 to 2000 ppm. And TDS sensor basically works in a concept that there is a two electrode, and between that two electrode there is a water, and if there is a high ionic solid dissolved there, there will be high conductivity, and if there is a low dissolved ions, then there will be less conductivity. This conductivity is will cause the high current. High conductivity will cause the high current, and low conductivity will cause the low current, and this current is converted into the voltage by the signal conditioning, and thus for low voltage there is a low ppm, and for high voltage there is a high ppm, no, yes, ppm, because that is that ppm is measured by the formula. We are measuring the electrical conductivity, and based on the electrical conductivity and multiplying it with certain factor, we will convert it to the TDS. So for high conductivity, that is high TDS, means there is a high total dissolved ionic solids, which will create a high voltage. So high voltage means high ppm, and low voltage means low ppm. In this way, this TDS sensor works. And We have another sensor, that is EC sensor, and EC sensor has also this similar type of working, like its voltage range is 0 to 3 volt. We can see here 0 to 3.3 volt, and I have explained that how it measures the EC, and this is a similar concept, and we move on to the PS sensor specification. PS sensor works. Um, Let me. PS sensor supply voltage is 5 volt, operating temperature is 0 degree Celsius to on 6 degree Celsius, and output specification is analog voltage, and 0 to 3 volt is the range, and PS range is 0 to 14. The working of the PS sensor includes there is a reference electrode, and also there is a glass electrode. In a reference electrode, there is a non-solution which will create a non-voltage, and based on the H plus concentration on the glass electrode, it will generate another voltage. The difference between that two voltage is the output of the sensor. Let's assume reference voltage is 100 millivolt, and the operating voltage range is minus 414 volt millivolt to 414 millivolt. That voltage range 0 to 3 volt is by signal conditioning, which will be done by the signal conditioning module, which will come with the PR sensor. And when the when the there is a reference voltage of 100 millivolt, and let's assume there is a H plus concentration which will create a 200 millivolt. So 200 minus 100 means 100 millivolt. There is a for high H plus there is a 100 millivolt. High H plus means low PS, and if there is a minus 50 millivolt, if there is 50 millivolt, then 50 minus 100 is equal to minus 50 millivolt. So this is for less H plus concentration. So for less H plus concentration, by single conditioning, it will give the low voltage, and for the high 100 millivolt, that is the high volt after single conditioning, will correspond to the which will correspond to the low PS. So there is a high voltage means low PS, and low voltage means high voltage means low PS. High voltage means low PS. Low voltage means high PS, because there is a less H plus concentration. So mm, in this way, we can see in the graph also, if there is a low voltage, there will be high PS. For low voltage, there is a high PS, because low voltage is generated when there is a less H plus concentration. Less H plus concentration means pH is high. Less H plus concentration is pH is high, and less H plus concentration means pH high, and less H plus concentration will generate a low voltage. So low voltage means high PS, and high voltage means low PS, which can be seen by the graph also. And this TS18B20 temperature sensor, this temperature sensor works All other sensor gives the analog output, but this sensor gives the digital output. So supply voltage is 3 to 5.5 volt, operating temperature -55 degrees Celsius to 125 degrees Celsius, output type digital, one wire protocol, resolution 9 bit to 11 to 12 bit, and accuracy is ±0.5 degrees Celsius under -10 degrees Celsius to 85 degrees Celsius. So it we have measured, we have done the calibration of the sensor, and we have done in 11 bit. The connection I will show there, and this sensor works basically on the concept that when the temperature changes, the resistance or voltage inside the sensor changes, and this analog is converted to digital by the ADC on chip, that is on sensor. And after converting digital to digital, it is sent to the Arduino, and Arduino will convert its analog value, and analog value is for us. And this sensor step size is calculated by the formula 0.5 by 2 to the power n minus 9, and is 11 for us because we have a measured in 11 bit. And this we can see there is a 125, there is a 1000 digital output. This is calculated by the formula digital output equals to temperature by digital output equals to temperature by step size. So this is measured by this, and we can see there is a linear graph for this. For higher digital value, there is a higher temperature. Okay, I have explained the electrical conductivity, and so far we have explained. I have explained this, and this is the sensory specifications. All suspended particles is measured by the LGZD sensor, so dissolved solid TDS meter. Ionic conductivity AC sensor, acidity and alkalinity is measured by the PS sensor, and temperature is measured by the D1B20 sensor. And all the other sensor gives the analog, and the temperature sensor gives the digital output. And we can see the range 0 to 1000 NTU, 0 to 2000 ppm, 0 to 20,000 microsiemens per centimeter, and 0 to 14 pH, -55 degrees Celsius to 1 plus 125 degrees Celsius. Linear graph is for AC sensor and temperature sensor, and with the positive slope, and negative slope is for PS sensor with linear graph, and non-linear graph for LGZD sensor and TDS meter version 1.0. And we have done this specification, we have gained the specification knowledge, and now this project is moves on like literature. We have done the literature review and parameter selection and sensor selection, we have done, and individual sensor we will calibrate, and then we will integrate all the sensor in one system, and this is the system integration and validation. After integrating this, we will made a we already made the noded display, and we will see the display, and after calculating the different parameters value, we will measure a certain WQI value, which is the water quality index, and this will generate what is the quality of water, it is good or bad or scalable or whatever. Okay, this is the block diagram, water sources. We have we will use sensors like turbidity sensor, PS sensor with single conditioning, TDS sensor, EC sensor, temperature sensor, and then it is sent to the microcontroller unit and then display unit. And this is the new thing we have done so far. WHO standard SI. This is the WHO standard SI for the water quality. No, drinking water quality. So turbidity, this is the range. This is the WHO standard. So we have this SI is reciprocated, and then WI is calculated by formula K by SI. K is the summation of 1 by SI. K is calculated by something. K is calculated by the summation 1 by summation of SI, means 1 by summation of SI something. This is calculated as a K, and this K Water quality rating formula, that there is a QI is calculated by on the value we will get, and SI, there is a SI in the box, and QI is calculated by this formula, and WQI is calculated by the summation of the WI and QI from this. And okay, WI is calculated there. WI is calculated there, and by the measured value of us, we can calculate the QI, and after some summation of this, we will know how much is the WQI, and based on that, we can determine what is the condition of the water. It is good or bad, or something like that. So after measuring the WQI range, we can determine what is the quality. It is safe or warning level or high risk level. That is the thing we have done in the node rate. This is the EC sensor simulation we have done. We haven't got the EC sensor in the simulation, so we have done it in by a potentiometer. Potentiometer is giving a voltage range, and corresponding to that, EC sensor gives the value. Similarly, temperature sensor. I have not explained the pull-up resistor. Okay, temperature sensor works on a high-low concept. So it is default low by the pull-up resistor. It is connected to the VCC, and output pin is connected to the 4. So it will default be high, and if there is a low, it will go low, and if there is not low, then defaultly it will be high. In this way, this works. Temperature sensor works. PI sensor, similarly, we have gained the output voltage range through potentiometer, and then corresponding pH is calculated, corresponding TDS is calculated, corresponding turbidity is calculated, and this wiring is for LED, and the potentiometer wiring is VCC ground, and then output to A0. Okay. Calibration, we have done the temperature sensor calibration. In the calibration section, there is a model equation. We have used x plus 0.73, and before calibration we have got the error of 1.62, and after calibrating with this equation, we have found the error to be reduced, that is 1.13%, which will ensure the reliable temperature compensation. Okay, this is the true temperature, measured temperature, and then we are calibrated by the formula, by the equation, and then we got this error, and all other status is passed under 1.5% error range, and 2 are failed, which can be compensated. This is the figure. This is the this is in the lab. We done the temperature sensor calibration. This is the in this conical flux there is a temperature sensor. We have measured the temperature, and then we read it in a Arduino serial monitor, and then we calibrated this. This is the node rate display. In the node rate display, there is a sensor value generation, and we will see in a gauge, and the trend also seen in the graph, and water quality status, for what level of water what level of WKI it should be, good or risky. It is done in this. This is the live parameters: temperature, pH, turbidity, TDS, and EC. This is the warning level of measurement. This is the safe level of measurement. We will do this in a in live. We will show it. This is the Gantt chart we have done so far. So this needs to be black, because final defense first is going to be held. Okay, accomplished. Parameters finalized, sensor selected, and testing of temperature sensor is done, and temperature sensor calibration is also completed, and architecture is finalized. So we have done the. This is something Okay. Future work is sensor testing and calibration. Integrate all sensors into a single hardware platform. Implement real-time data logging, long-term field testing. Improve calibration for PHEC and TDS. And we will also planning to do LED indication. If there is a risky level of water, then we will make a LED, red LED blink, red LED showing, and for warning there is a yellow light, and for safe there is a green light. So incorporate LED indicators to show different colors based on the measured levels. So thank you for listening, and this is all we have added in this final presentation. This is not the final. This is the 1 year project, and for 6 months this work we have done so far, and this is the end of the 5th semester. And thank you very much for listening. For further information, you can contact any of the team members, and thank you very much. Namaste.